been a few months since I did a video, and I really wanted to talk you through the progress update on the modular biped. Now, as you may know, I've been working on this thing for a few years. I'm on probably version 3 or 4 now, and what I'm looking to do is try and build a more robust version of this project that will walk ideally, or at least be able to stand and balance and animate in a way that the previous versions couldn't. I also have some quite interesting ideas for new technology that I want to add. So I'm going to walk you through all of the updates and all of the changes since the last video, which I think was probably in the first half of last year. So there's quite a lot to get through. I'll try and put sections in the video so you can skip ahead if you're not interested in a specific thing. But yeah, let's take a look. This video is sponsored by PCBWay. More about that later. So, this is the guy. As things stand at the moment, there are a few things that I'd like to be able to build on. Obviously, this is very much a work in progress, but I appreciate that the last time that you saw this, it was in fact just a PCB. So just to recap, this is a modular biped robot. I have built this from scratch pretty much, using Python, using Arduinos, Raspberry Pis. Started out with the Raspberry Pi 3B Plus and then moved into the Raspberry Pi 5, and then more recently in this version I'm actually using the Compute Module 5, which is a small industrial board that doesn't have any of the USB sockets and that kind of thing. And what you do instead is plug it into a carrier board, and the carrier board allows you to break out all of the functionality that you need while keeping the form factor very small. There are a couple of videos on building that companion carrier board. And what I'd like you to do, if you haven't seen those, is maybe go back and take a look at that, because I'm not going to go into the detail on the board itself. But just to say that this black mohawk looking thing on the top is actually the heatsink for the CM5, the Compute Module 5 board, which is under here. And then there is also, if I open this up, hopefully you can see, there is also the custom PCB there with the camera attached and all of the wiring going into that in order to control things. And you can see at the moment everything in there is looking quite kind of compact. And this, believe it or not, is as neat as I can get it. So what have I built on top of that CM5 board? There is a TFT display that's used for the eye, and there is a graphic, which I'll show you later, that allows the eye to animate and express certain emotions. There is a Raspberry Pi AI enabled camera, and that camera is actually supposed to, and does quite well, people recognition, object recognition, gesture recognition, pose estimation, and different things like that. And the load on the Raspberry Pi is lessened because the board itself actually has the chips in order to do that work. And it's a kind of more or less like for like replacement in terms of form factor for some of the other Raspberry Pi cameras. So really worthwhile getting if you're into that kind of thing and you want that to be part of your design, your robot. On the side here you can see I actually have a push switch. If I show you on there, you can see a couple of modules on either side as well. So the push switch is to start and stop the Raspberry Pi. So it's wired up to the actual power switch that the CM5 comes with, or rather the ability to add a power switch that the CM5 comes with. And you'll remember if you have a Raspberry Pi 5 that actually has the power switch integrated onto the board. This is my breakout of that same functionality. And down the side, what I have here is a microwave sensor. So that is a little bit like a PIR sensor that can detect motion, except it doesn't need line of sight, and it actually works kind of through walls, through solid material. So the idea with that is that if this board detects that nobody is around, we start a timer. And if nobody's around moving for a set amount of time, I can actually make the project go to sleep or even shut down. So useful for power saving and just generally other animations. This is an inertial measurement unit. This is the MPU 6050, not the best one. I understand that there are better inertial measurement units out there now. This allows you to detect the position and acceleration of the head as it moves around, which is useful for balance. Inside here we've actually also got a speaker, so that connects to an I2S amplifier, which I created as part of that custom PCB carrier board. And then there's also dual MEMS microphones, which are also I2S integrated into the board. So in other words, what that means is that the robot can hear, and it can hear in stereo, and then it can also output through that mono speaker. The antenna is the antenna that is the official Raspberry Pi CM5 external antenna, and that plugs in directly to the CM5 itself. What that does is it effectively means that the signal, rather than using the internal antenna on the Compute Module 5, it uses this external antenna. Now that's going to be useful in the future. The plan is maybe to make this out of aluminium in order to make it more sturdy, but also to act as a heat sink to dissipate the heat from the Raspberry Pi. It should also animate. So you may be able to see within here, if I move all of this out of the way, very much down at the bottom. See if I can get you to focus on that. Probably not. There are gears in there. And the way that the gears work is they should allow a servo to move this. And I actually have it so that it can actuate, but I didn't have room for the servo in this version. So in the new version, what I may do is actually upgrade that in order to have that servo moving. Just a note on the heatsink, there was a point where I was running the program flat out, where it was doing everything it could possibly do without any kind of breaks or sleeping or anything like that, and the Raspberry Pi overheated and it got to something like 80 degrees. Now, I do actually have software to manage that, so it will throttle if that's the situation, and if it continues to get warmer and warmer, it will actually shut down the program, in which case the idling CM5 doesn't tend to have a problem with overheating. But what I've also just bought, and it arrived in the mail today, is this. Give me a second. Is this, and it is a CM5 heatsink, but it also includes an integrated fan. Now what you can do is have an output from the CM5 to control the fan, so it doesn't have to run at full speed all the time. It runs depending on the heat that's dissipated from the Pi and the temperature of the Pi itself. The only problem is my version of the board doesn't have this connector because I didn't think that I would need it. So I'm planning on probably creating a new version of the board that just moves some of the headers around so that I can make sure that I'm actually fitting everything in a little bit easier, because a couple of them are quite cramped, and then also integrating things like this that I didn't appreciate I needed the first time round. Just on that note, you can see there's a number of JST connectors connecting the board inside. They've worked really well, and they're actually half size compared to the standard headers that you would get on a Raspberry Pi 5. So they save space, but they still allow for that data signal. The thicker wires you can see there are all to do with power, and I've tried to almost over-engineer it to make sure that we actually have the ability to power everything without any brownouts or any issues around power delivery. And on that note, on the back of the board, or on the back of the head, is this, which is a new DC to DC converter. So I previously had DC to DC converters that worked with maybe 5 amps max. But unfortunately, the Raspberry Pi is quite power hungry, and at peak current, it can draw more than that, or around that amount anyway. So this is a new board that can handle up to 10 amps. Useful, very large, obviously, compared to the other one that I had, but seems to be working really well. And then finally on the head, you'll notice that I have this little laser emitter. Now what this is a detachable module. So this is a magnetic connector with 4 pins. So you have the power, that's positive and negative, and then you have 2 other pins. One of them is for output and one of them is for input, and they're mapped to 2 GPIO pins on the Raspberry Pi. So for input, I could potentially make a module that reads temperature or radiation or any other kind of analog input or digital input for that matter, and snap it on the side, and it will connect to the input GPIO pin. And then in software, I can tell it to run a different mode depending on what it is that I have connected. Then on the other pin, the output pin, I can have things like this, where you can snap something on and have it project a laser. Now in this case, it's actually a laser line, and the idea was to kind of create a laser scanning animation so that it could scan objects in front of it. The problem is that the power requirements of some of these modules is higher than the GPIO pins can draw directly. So what I actually have is a fairly high current capable transistor in line with that, so that when you toggle it on using the GPIO pin output, it actually draws the power directly from that DC to DC converter and can supply enough current, not a lot, but enough current that some of these small modules can be powered. So I'm really interested to see what I can do with that detachable module idea. There are a few things that I already have planned to build. For example, I have a infrared emitter that I can obviously use, or an infrared receiver. So I could potentially build a module that does both, where you can program it with your remote control and then have it control the TV or something else like that. So there's a few different things that I can attach to that. And I really just want to have a play once I've got the rest of the build created. Now you may have noticed as I've been doing that it's been quite cramped inside that head, and the reason for that is that I designed it with an estimation of how much space I would need, but in actual fact there is really an argument that I should have made it slightly bigger. Similarly, as I've been working on the design, it really does look like I could do with a larger head because it looks disproportionately small to the body once the body's in place, which I'll show you. The neck at the moment is static, so there's just a pin that allows it to move up and down manually when I move it with my hand. What I have been working on and starting to 3D print is a design for something that allows me to not only rotate the head, and it's using a mechanism called a lazy Susan, which is effectively just a large bearing with a hole in the center. So I'll be able to rotate the head around the bottom plate with the wires passing through this guide, the sort of circle around the outside edge there. But it also is going to have two servos, one for one side and one for the other side of the head, which is going to have connectors to the bottom of the head. And so what that means is that as this point pivots, it can also move the head up and down by moving both at the same time, or move one and not the other, or move them in different directions to have the head pivot on a universal connector, which will be at the back. And hopefully I'll be able to get more of that completed so I can talk about that in the next video. I'm waiting for those parts to arrive, but obviously once that's in place, it'll give me a good idea of what the rest of the build should look like. I've also been working, as you can see, on legs. Now the previous servos that I had were hobby servos, and the hobby servos were really quite limited. They were fairly capable in terms of torque. The stall torque was sufficient to be able to hold the entire legs in place and the body and that kind of thing. But it didn't understand what position each of the servos had. There was no feedback on the position of each servo. There were no kind of smart functionality around over torquing them and that kind of thing. So I've started switching out the hobby servos for these. These are bus servos or serial servos, serial bus servos I've heard them called. And what you do with these is you connect them all in line. So this may look like a jumble of wires down here, but actually what we have is each servo is connected to the next in series, in serial, and then from that it makes its way to a controller board. And you can see I have a controller board here which actually has two inputs and outputs, and that's because I've got one that's using the connection to the smaller servos which connect to this junction box, and then one that goes to both legs because they're all connected together. These little junction boxes are useful because they allow me to connect more than just the two different paths if I need to do that, because I want to have them coming from two different origin points, so I effectively need a joint or two places to plug them in. And then the neck similarly is going to have three different servos that all need to be connected in series in order to make that work as well. So this driver board is actually really straightforward. It has the power coming in here. There's also the option to connect via USB, which means you can connect it directly to your laptop in terms of programming, or if you change these header connections, you can connect via this, which is the UART or serial connection directly from the Raspberry Pi. So you can see I've kind of jerry-rigged a cable here from the Raspberry Pi serial output to the board and then connected the servos in there. That then connects to the DC to DC converter that I was talking about that can handle about 5 amps, and that seems to be sufficient, and if not, it's easy enough to upgrade. And then finally I have a USB-C power delivery trigger board where you can set the voltage between 5 and 20 volts. And when you plug in a USB-C with a capable power adapter, you can actually get that voltage and therefore that appropriate amount of power into your into your board. So you'll notice there are two DC to DC converters in the project, one for the head and one for the legs. I did the same thing on the previous version, and that I found just helped avoid any kind of power delivery issues, stopped the Raspberry Pi from blacking out or browning out because of the servos moving particularly quickly or anything like that. So one of the key changes in this version is that there isn't an Arduino. Now, in the previous version, the Arduino controlled the legs directly, and then there was a serial connection between the Raspberry Pi and the Arduino in order to facilitate the instructions. So I want to move forward, I want to lift the left leg, I want to do whatever. Or you could directly control the servos, but that command was interpreted by the code in the Arduino, and then it was enacted by the driver in the Arduino software. Now the challenge with that, I found, was that if I needed to make a small change to the Arduino code, I needed to log into the Raspberry Pi and deploy it via the Arduino IDE on the Raspberry Pi, which was a bit of a pain. So what I was hoping to do for this version, since I had the option to include this new serial controller board, is do away with the Arduino and effectively just have it so that everything was controlled by the Raspberry Pi. Now, I don't know that that's the right choice. I'm not 100% sold on that idea. What I may do is use an ESP32 board or an Arduino, and I'll have that communicate with the Raspberry Pi again, and then have a situation where the Arduino or ESP32 controls this driver board. I may also look to create a custom board that incorporates all of these components into the body, because at the moment there's a lot to fit in there with all of these larger boards, whereas making a single one that could work specifically for this build would be quite useful. I also would very much like to have an I2C output where we do have capability of outputting that from the Raspberry Pi, and I'll feed that into the body, and that will allow me to put like small displays in place or IMUs on the body rather than just in the head. And the other thing that I really wanted to try was this. So this is an electromagnet, and the way that this works is that you apply power to it and it creates a magnetic field which will bind that magnet to any metallic surfaces that react to magnets. This is a test foot. This is definitely not the final version because I don't like this at all. But the idea was to power this up and stick it to things and see how well it held, and see whether I could engineer a foot that when powered would stick to metal. Now, why is that important? Well, the advantage is not so much to allow it to walk on metallic surfaces, but because I had the idea. With my previous version, I had a backpack that the feet could clip into, and then when I went to events, I could carry the robot around on my back. The challenge with that was really that it was fiddly to get it connected to, and I didn't really like that mechanism. So what I'm hoping to do now is actually utilize the electromagnets and create some form of metallic wearable, like a waistcoat or a backpack or something, and actually be able to pass the robot up to the backpack and have it clip in place easily, and similarly detach easily when I want to be able to take it off to show people. Now that may just be a pipe dream, but it's a fun thing to try, and if it doesn't work out, I can easily just redesign the legs again. Now, because of the potential backlash from powering and disabling these, I am putting relays in place, which again, we need to find space to fit them in. And then I also may have some form of detection of pressure on the feet, which will be useful not just for this, but for also the kind of potential walking algorithms and that kind of thing in future. So the servos have been built with primarily wave share servos. These are the ST3215 servos. I'm currently powering them with somewhere in the region of 8 volts, so it's not... the previous project, I think everything ran on 5 volts, and this one it isn't necessarily the case. Similarly, the smaller servos, the SC09 servos, have a slightly different voltage range to the larger ones. I also have a mix of manufacturers, and that all seems to be working really well. So the good thing about that is it doesn't particularly matter which manufacturer you buy them from, certainly from the things that I've tried. The software will work in either case with either of the servo manufacturers that I've attempted this through. There is also an ESP32 enabled version of this board, which allows you to connect the servos directly to an ESP32 if you'd like to do that rather than have to have this with the manual connection to the Raspberry Pi. The legs are connected with fairly small pieces of 3D printed plastic. Now, the problem with this is really weak and they are quite prone to breaking. What I wanted to do was create a configurable set of components so that I could connect these in any number of different ways. And you can see on OnShape, I've actually gone through and tried a few different versions of this to try and understand how do I want this to work? How do I want this to be configured so that I can get that the best ability to do what it is that I want it to do. Previous versions, it couldn't sit down. This one, it can splay the legs out in front and actually sit on its lower part of the body. The plan for these really is not to 3D print them in plastic, but actually... So the plan is to 3D print these joints out of metal once I have the final design created. But I will say they have held up pretty well considering they're incredibly thin slivers of PLA+. They're also mounted together through a fairly standard format which actually mimics the servos themselves. So the servos actually have 4 screws, ignoring the center screw, at a specific spacing around the spline. And all I've done is copied that design and included it on all of the other joints. So it means that the servos can connect to joints and joints can connect to other joints, all without any real issues. The servos can be pretty easily configured. The one thing to note in terms of a change here is that the servos actually rely on having a unique identifier, which makes sense because they're all connected to the same serial bus. So once you buy your servos, you need to give them all a unique ID, ensuring that none of them have the same ID as any of the other servos in the project. That applies to both the ST and SC, in other words, the larger and smaller servos. And then once you've done that, you can run the configuration through code. And I actually have the option to calibrate them, so you manually move them to their extremes of range, and then set those ranges in code so that they won't exceed them and it's safe and you won't be able to drive them past those endpoints, which is a feature I really like because it's one of those things that was a real challenge with the previous servos. You also have the ability to detect the starting position. So one of the characteristics of the previous build was when you started it up, all of the servos would snap to those initial positions that you had programmed, whereas with this one you actually have the ability to say, detect the current position and then move smoothly to the starting position, or maybe even don't move smoothly and based on the position that you're in detect that you're sitting or standing or whatever it might be and behave differently based on that, which is a really exciting opportunity to kind of build on what we already had on the previous version of this. One of the other things that I've added into the functionality is the ability to control the project remotely. So I actually have Xbox Series S/X controller, one of the newer Xbox controllers, connected via Bluetooth. And after a little bit of fiddling around, I managed to make it so that you can control the eye animation, you can control the servos, and you can control and configure what you control via the config file. So for example, if you want to make it so that pressing the trigger buttons makes the legs move up and down, you can change that with a couple of lines in the configuration file and have it work immediately. I also took it a step further and made it so that I can record any input. So in other words, I can record animations that I tell it to do through the controller and then play them back later, which will be really useful when we come to starting to kind of animate and react to user input and that kind of thing. Now the plan is not to make it a puppet, the plan is to make it fully autonomous, but I identify and recognize that really what I need is the ability to teach it how to behave, and the controller, the gamepad is really the way to do that. I'm drawing inspiration here from some of the other things, such as the Ricci Mini from Pollen Robotics, where they really have focused on the animation and making something feel lifelike, which is something that I really wanted to achieve with this. So what I'm hoping to do is kind of leverage some of that understanding and really build something that behaves as if it is alive in this version. So one of the big questions I always get is around making it walk. I've kind of mentioned that that is one of the long-term goals of the project, but I will admit it isn't my first priority. If I can make this thing behave in the way that I want it to behave and become a fully functioning companion robot, I'd be happy if it didn't walk. The good news is that the hardware that I have now is really getting to the point where you can achieve walking with this build. Now, we've seen this in other builds. Disney released a droid that they take around the theme parks, and a few people have been really keen to have one of them themselves. So they've built not only the full-size equivalent as an open source project, but also what they call the BDX Mini, which is using the same servos in a similar configuration, and it allows them to use machine learning to train it to walk. So that's a project that you can build today with a similar kind of cost to this one. Now, I'm not looking to just copy that project in order to make it walk. My goals are slightly different in terms of the way it looks and feels and behaves, but I really like drawing inspiration from that, and I have taken a look at that project as an opportunity to potentially build in the future. I'll leave a link in the description so that you can take a look at that. We also have a few people working on training the robot to walk, and this is for the previous release, the body release, but with these servos. So the new serial bus servos in the old legs and the old body in order to achieve that same goal. And it's looking great so far. Progress is obviously ongoing. If you'd like to take a look at that and maybe even help out, then feel free to join the community. Another thing you may have noticed is that there are no batteries currently. The previous one was running on 3 18650 lithium-ion batteries, and that worked really well. It gave me a few hours of battery life. I'm hoping to improve on that so that I still have those batteries in place, but I also have the ability to either hot swap or connect mains and have it switch while live, or even potentially charge. And these are things that I'll look at as kind of further developments in the future. Yeah, ideally I'd like to have it plugged in and running, and then disconnect it from the mains power and have it switch automatically to the batteries. And then obviously when plugged back in again, in an ideal world, charge. But I don't know that I trust myself with charging lithium-ion batteries inside the project. So we'll see about that one. So what are the next steps? Well, I can basically redesign the entire thing with all of the information that I've got from this one. It has been a brilliant project to work on over the last few months. Am I happy with everything? No, not at all. I have some ideas for the best way to reconfigure the legs. I have a better idea for the feet. I have some idea of how I'm going to do the body, and I'm looking forward to trying that out. And then once you've put all of that together, it looks as though the head is actually too small. Now that's interesting because the reason why I went with the CM5 was to try and make the head as small as possible, but aesthetically it looks strange once you've assembled everything. So I'm probably going to create a new version of the head, and that version is probably going to incorporate some of the neck servos to get them out of the way so that it can look a little bit more finished and professional. So there is plenty more work to do before I release this as a finished version, but I hope that that has given you at least a reasonable idea of where I am with the project and why it is that it's taken so long. There's been a huge amount of work around understanding how all of these new components work. It is effectively like starting from scratch because nothing from the original project has actually survived to go into this one. I want to thank PCBWay for sponsoring the video. As always, they're one of my long-term sponsors. I've been continuously impressed with the products that I've had manufactured there. I've had everything from PCBs to metal 3D prints created. The service is always great. The shipping time is more than fast enough for what I need, and it allows me to build things that I otherwise wouldn't be able to build. They also offer a PCBA service, that is assembled PCBs, which I may be utilizing in future if I'd like to start mass producing the carrier boards. So hopefully that gives you a good overview of where I've been and the kind of journey that I've been on with this project over the last few months. If you have any questions, feel free to reach out. We have a GitHub repository that has a discussion group, so feel free to post on there. Otherwise, I will be updating the documentation both on the GitHub wiki and also on the MakerForge website, which is makerforge.tech, link in the description. Thanks for watching.